things. First, Adam. So Adam White, who is one of the persons putting together the Coursera courses, you know him from the videos. He's going to be lecturing for the next 3 lectures, where he comes to class and then you are going to solve problems together. I think it's kind of that thing that he's going to do mostly, because I will be away in Hungary. Unfortunately, we have some family events that makes us go back to Hungary. So I won't be here, but Adam is going to be here and he's going to submit. Okay, so that's the first thing. And then today, we go back to TD0 convergence with linear function approximation. And we'll finish the argument there and talk about, it's going to be related to fixed points of operators. And we're going to talk about the properties of the fixed point that we can get from TD0. And then maybe, time permitting, we are going to talk about something else, like some modern stuff, DQN, deep Q networks. That's kind of a fun topic. All right, that's it. So I'll be back next Wednesday, not this Wednesday. Okay, TD0 convergence with linear function approximation. You have to start over putting all the notation on the board. So what did we have? We had a feature map that was mapping the state space to d-dimensional vectors. And then we had the TD0 update equation that was saying that the next parameter vector is equal to the previous parameter vector plus alpha times the TD error. I don't remember. I use T plus 1 here or T? T? Okay, let's be consistent with that. Times xt. Xt is the feature vector at time t, because this algorithm is run against this trajectory. Of data, states, actions, rewards, states, actions, rewards, where the actions are generated by following a policy, which we fix. It's a memoryless stochastic policy, and the rewards and the next states are generated from the transition kernel of the MDP that we fix at the beginning. It's a finite MDP. And what's missing still is the definition of the TD error. And the TD error definition is just that you make a prediction of what the total discounted value is going to be given your current estimate and the experience transition. So the experience transition is that, oh, we are at state ST. We just went to state ST plus 1 and incur this reward RT plus 1. So use the reward plus gamma times the value of the next state that you arrive at. And so that's the prediction. And you compare that to the value that you currently have. So this creates an error between a predicted value and the current error, the current value, where v of t is this function that's real valued, which for a given state assigns the value of the inner product between the weight vector theta and the feature vector of the state. Okay, everything's on the board. This was just reciting stuff. Okay. Good. Any questions? We're all good. So then the next step was that I said that, okay, assume that the initial state is distributed according to some distribution mu. So this mu distribution is a stationary distribution of the Markov chain that's formed by just looking at the states in this data. And the transition dynamics for this Markov chain is described by this Markov matrix or stochastic matrix that is an S by S matrix, and the SS prime element of it is just gives you the probability of transitioning from state S to state S prime, given that you start at state S, choose an action according to pi, and then follow the transitions in the MDP. And this probability can be calculated this way, summing over all possible actions. And then we introduce this function f, which was mapping RD to R. And where we just looked at this expression, like this is how theta is moved, the direction in which theta is moved, the expected direction of the movement of theta. So f of theta is defined as the expected value of the TD at theta times the feature vector. So the TD error is real valued. We are comparing two predictions. Both are real valued. We are subtracting them. So that's real valued. Xt is d-dimensional vector. So this is a RD to RD map. Okay. It's like a vector field. It's like, oh, you're at this theta vector. This is the direction you're moving into. Then I argued that in order to understand how TD works, a good starting point is to understand how this iteration is going to work. And maybe first we can look at the case when alpha is equal to 1. Even in that case, we expect this to kind of work because there is no noise now. Okay. And it turns out that after doing some math, we discovered that this iteration, this last iteration when alpha equals 1, is equivalent to, oh, sorry. So if we take a different view and we say that, okay, we have these value functions. So the t's value function is v of t dot t. And we care about how these value functions behave, not how the parameter vector behaves. Eventually, the parameterization, may change, but it's the value function that we care about. So we want to know how the value function behaves. So from this equation, you can derive how this behaves, and this is what we did the last time. So one holds if and only if Vt plus 1 is equal to the projection of applying the Bellman operator, Bellman policy evaluation operator to Vt. So this operator T pi of V is just R pi plus gamma times P of pi V, where R pi is just the immediate expected reward under policy pi. So R pi S is summing over action A of pi A given S RSA. And the projection operator does the following. Okay. So the projection operator, this pi, is an RD to, R to the S to the R to the S map, which takes an element in RS and returns an element of RS as dimensional vector such that this is equal to the minimum over theta of V theta minus U, where we consider all possible thetas, and this norm that we are using here is the so-called mu norm. It's a squared norm. So if you're squaring the norm, then the squared norm is equal to summing over our states mu s times u squared s. All right. So we got this far the last time that we derived all this. Okay. Next question. So we have this iteration where we are composing, first applying this Bellman operator, the policy evaluation operator, to define the current iterate, and then we're applying a projection, and then we iterate this way. So this is a fixed point iteration if this operator, the composite operator of pi and T pi together, if that has a fixed point, then this may converge to the fixed point of that operator. And the question is, okay, is there a fixed point? Is convergence going to happen? And what is the big tool that we always use in this class to understand these fixed point iterations and argue about that the fixed points exist? They're even unique. What's the name of the theorem? Or what's the tool? What's the name of the tool? It was briefly mentioned at the end of the last class. Yeah, the Banach's fixed point theorem, which tells us that if we have a norm over a Euclidean space, and we had a map that takes vectors of this Euclidean space, returns vectors of the Euclidean space, and this map is a contraction with respect to the norm, then the map is going to have a unique fixed point, and the fixed point iteration, the iteration of this type of repeatedly applying the map to some vector, ought to converge to the fixed point, and the convergence is all fast, and so on and so forth. That's Banach's fixed point theorem. So we want to apply this. Question is what norm to use, and well, we already have some norm here on the board. So it gives itself that maybe we should be using this norm. One could try to use, well, okay, maybe an idea before that would be to try to use the maximum norm, because the maximum norm is the norm that we used before. And we have shown that this Beaumont policy evaluation operator is a gamma contraction with respect to the maximum norm. So we already know that. So it might be, it might look like it's a good idea to push that and ask ourselves the question, okay, can we use the max norm? So if you try to use the max norm to analyze, so there is this operator, let's call it, I don't know, everything is a T, I don't know. What do you want to call it? F. Define F to be, first apply T pi and then apply pi. It's the composite operator. So if you try to apply, if you try to prove that F is a contraction with respect to the max norm, well, what comes to mind is that if you're composing operators, we had this little result that said that, oh, if one operator has a Lipschitz factor L1, the other one has a Lipschitz factor L2, then the composite operator's Lipschitz factor is at most L1 times L2. And so here, the Lipschitz factor for T pi is going to be gamma. If the Lipschitz factor for pi would be something such that you multiply it with gamma, you get something smaller than 1, strictly smaller than 1, you would be good. Unfortunately, that's not the case. So the max norm is not going to cut it. So the second idea is that maybe the mu norm is going to be a good norm. The question is whether the mu norm is really a good norm. And there we can apply, we can try to follow through with the same reasoning. We have this composite operator. If T pi was somehow magically a gamma contraction with respect to the mu norm, and pi had good properties, let's say it's a non-expansion, so that means its Lipschitz factor is less than 1 with respect to the mu norm, we would be done. And okay, projections with respect to Euclidean norm like this, this is a variation of the squared norm. This is just a weighted squared norm. They do have this property. So it's like, okay, people who first thought about this, they kind of already knew that the projection is going to satisfy this property, that it doesn't increase its distances. And to convince yourself that that's the case, you can draw a little picture. So with the standard Euclidean geometry, the picture would look like something like this. So you have the high dimensional space. So we can only draw a picture in 2 dimensions. So there are 2 states. This is RS. So this would be RS, but okay, we can only draw this picture for s equals 2. So there are kind of 2 states. And so every wave function is just a point here. Okay. So what the projection does is that, let's look at the definition of the projection. Where is it? It's here. It tries to come up with a new vector. So given some vector, let's say this. This is my u. So I have 2 components here, u1 and u2. This is just called u. What it does is that it tries to find the closest point to it here, but only amongst these guys. So functions that can be expressed as v theta. Okay. So what are these functions? So v theta as a vector, it's an s-dimensional vector, can also be written as x times theta, where x is this big matrix that you form by listing all the feature vectors corresponding to all the S, capital S states. Stacked on the top of each other. So you have to first transpose the two to make the dimensions work. So if you do this, you form this big matrix. This is an S by D matrix. Then look, if you multiply x with theta, you have the first vector you multiply out with theta. Let me just animate this for you. So you have one vector, and you have the last vector, and you have theta here. You just have theta. So you have to multiply the first row with this column, and that's what you write down as the first entry. So that's x transpose 1 theta. So that's the first entry in the multiplication. And the very last one is going to be x transpose s theta, which is just v theta. All right? So I didn't do anything. I was just like reformalizing the definition of v theta. Why is it useful? Why is this useful? Well, now we can think about all these vectors, so the set of all v thetas such that theta is d-dimensional is the same thing as the set of x theta, where theta ranges over all the d-dimensional points. Okay. So that's called a linear subspace. It has d degrees of freedom if all the feature vectors are linearly independent of each other. The d-dimensional subspace, this is a subspace of R to the S. So we have this high-dimensional subspace. Okay, I just two now, but it's high-dimensional. And you take, that's S-dimensional, you take a d-dimensional subspace in it. Okay. So d-dimensional subspace is, how do you imagine that? Well, in our picture, S is 2. So if I want D to be smaller than S, I don't have any much choice than to choose D equals 1, because if I choose D equals 0, that's a trivial case. We don't consider, you would have no parameters. The only choice I can have is D equals 1. So what are the one-dimensional subspaces? But these are the lines through the origin, right? So when D equals 1, we have one weight vector. So all the feature vectors are going to be one-dimensional, and all of them line up, right? Like we can just like take this vector, take its multiple, twice as big, 3 times as big, and so that's the weighting, all right? And so it passes through the origin. So the general picture is this. This is this subspace. How do I call it? Capital V. All right. So this capital V is the subspace in RS. And in our picture, D equals 1. So it's just going to be a line. OK? So far, so good? Now, we said that, OK, we take whatever vector we want to have a representation for, U, and we take the closest approximation of it amongst all these functions that we can represent. So that means just choosing a point in this subspace which is the closest to U. What does that mean, closest? Let's say as we use the standard Euclidean geometry. So the closest in the standard Euclidean geometry, it's intuitively speaking, you should be getting it by taking the point here within V, this point little v here, such that the vector that goes from 0 to v, so that the v vector, and this guy here, that orthogonal to each other, right? Sometimes it's called a Pythagorean theorem, and so on and so forth. It has various names. That this is the best possible approximation that you can get. You will get this orthogonality property there. So this means that u minus v is orthogonal to v, where v is the projection of u to the subspace capital V. Okay? So I just gave this a name. So we have the vector u, we have the vector v. So this vector here, this is u minus, I mean, like, okay, this would be this vector. You shift it back to origin. But I can also draw it here. So that's u minus v. So that vector is orthogonal to v. Okay. So this holds for the weighted norm as well, not too surprisingly. So it's going to hold that this guy is orthogonal with, but the notion of orthogonality somehow changes. So orthogonality in standard Euclidean geometry, so two vectors are orthogonal to each other. In the standard Euclidean geometry, what's the meaning of that? Meaning of that was that the net product between the two is equal to 0. So for 2 norm, u orthogonal to v in the 2 norm geometry means that u transpose v is equal to 0. If we write it out, we saw everything is indexed by s. So that just means that us times vs summed over all possible s's is equal to 0. So the analog notion, if you have weighted norms, is to take a weighted inner product. Okay? So for the mu norm, okay, so this norm, if I want to emphasize that the mu plays a role here, I just put a mu in the index. Okay? So for the mu norm, the orthogonality with respect to this mu norm means that if I'm summing over the states, but you take the product of us and vs, but you need to weight it with mu s, then you're going to get 0. So now we have pretty much all the pieces of the puzzle. For the first thing that we want to show, which is that we want to claim that pi is a non-expansion or one Lipschitz function with respect to this mu norm. Okay. How do we do this? Well, the proof is kind of here, is on the on this figure already. Except that, okay, this is for Euclidean geometry, but an analog figure holds for mu norms, this weighted Euclidean geometries. So what do we need to show? You take this vector u, you take its length, and you want to argue that after you project it to the subspace, you get a vector whose length is not more than the length of the original vector. Okay? So we have this vector, and this is its length, u, the length of u. And we project it. After that, we get this length. This is the length of v, the projection of u to this subspace v. We want to argue that the length of v cannot be more than the length of u. You look at the figure, what do we have there? We have a nice triangle. No. So we have this triangle. Yeah. No question? Okay. So we have a nice triangle. Said that my marker doesn't work. You see the triangle? Okay, let's see. This marker works. Oh, this works better. So we have this triangle. And it has a right angle in that very corner. So what do we know from geometry class about triangles? The length of a right angle triangle. Yes?
The hypotenuse is always longer or equal to other.
Yes. The hypotenuse, the longer side, is actually longer. But Pythagorean's theorem actually would say something like square this plus square that is equal to square that. Right? So that's still true here. So u minus pi mu squared plus pi u squared is equal to u squared. From which it clearly follows that u, the length of u, is at least as long, as big as the length of any of these two guys in particle of pi u, right? So then you can just rearrange. Sorry. Pi u. I have to subtract something. Okay. So that this holds, this relation holds, that holds exactly because here we use that u minus pi u is orthogonal in this mu orthogonality business with respect to pi mu. So if you want to show algebraically that this holds, then you just have to use this. Why does that hold? Well, there is a little calculation that you can do that shows that that also holds. All right, so this shows that pi is a non-expansion. Yes? You're talking about this triangle here?
Yeah, I mean, like the mu orthogonality is the same or corresponds to the geometric target.
What was the question?
We know Pythagoras for like a geometric triangle.
Yeah.
Have like orthogonal here, but it's orthogonal with the mu. It doesn't
Right.
correspond to the geometry.
Well, you can argue in many ways. You can argue algebraically. Just basically, the algebra works out. Or you can try to transform one geometry to the other. Actually, there is a very simple transformation of the geometries. So if you think about the difference between the geometries with respect to the standard 2 norm and the mu norm, it's just the scaling with the mu. Every axis is scaled with respect to mu in a way. So you can rescale back, and then you get back the Euclidean geometry. So the only difference between this mu-weighted geometry and the other geometry is that the unit circle in the normal geometry, which determines that like where this projection is going to be, in the non-weighted geometry, it's an ellipsoid, where the ellipsoid is compressed differently according to the different directions according to mu. It's like you have to divide by square root mu to get the Euclidean geometry. Yeah. And then the same pictures apply. So you can have picture-based proofs too. OK. So we're done with that. So the next question is, OK, this is progress. Yeah. Is that what? Well, pi had to be this projection with respect to the mu norm. And that implies that it's a linear operator. This is not general. I'm like, we choose the mu norm, then the mu norm gives you the definition of pi. The proof itself at no step used the linear property of pi, but it uses the definition of pi, and pi is linear, so I don't know. Yeah? Oh, okay, so that part. Okay, yeah, sure. Yeah, true. Okay, yeah, that's helpful. Okay, so you're talking about that. Okay, I'm leaving out one step here, which is that, okay, in general, non-expansion just means it's one Lipschitz. One Lipschitz just means that different color for all u and v, you have to show that pi u minus pi v in your chosen norm is less than equal to the distance between u and v. So things are pulled together. And how do I prove this? Well, I notice that pi is linear. So pi u minus pi v is pi u minus v. OK. You have to prove it that it's linear, but yeah. Because the only definition that we have at this stage is this. From this, it's not obvious that it's going to be linear, but it's linear. OK, and then we have this inequality that, OK, this is upper bounded by just u minus v. which is what we wanted to have. So you also have to use linearity. Thanks for noticing. I was about to skip that. Yeah, this part of the proof didn't use anything about linearity. Somehow I saw that you're asking about that. The whole proof needs to use that pi is linear. Okay. So let's go to t pi. So let's show that t pi is a gamma contraction. So that's the miraculous thing. Okay. So proof. Take u and v in Rs. Start to calculate t pi u minus t pi v, the difference between the two. You plug in the definition of t pi. Okay, the r pi is going to cancel. The gamma comes out because mu is a norm. And we end up with this. So we see that what we need to show is that p of pi is a non-expansion. Okay. So let's calculate p of pi at the function u, the norm of this squared. So just writing the definition. This is just plugging in the definition of the norm and plugging in what it means to apply this matrix to this vector. So matrix vector product, you got an element, and then you just have this. OK, so now comes the tricky part. You need to know something, like your elders are telling you, if you move the square inside of an expression where you are summing over some probabilities, so these are probabilities in S prime. They sum to 1. They are non-negative. And if you move the square inside, so not squaring the probabilities, but squaring these values, then you get something bigger. You cannot ever get something smaller. So moving the square inside, you get something bigger. That's a special case of Jensen's inequality. If you have heard about Cauchy-Schwarz, it would follow from Cauchy-Schwarz as well. But this is something that you learn at one stage or not. No, I'm telling you, if you haven't heard about it, that this is true. This is a beautiful step in the proof. So now we have moved the square inside, and we have this double sum. And we can swap the order of the two sums. And this is what we're going to do. So we have S prime. That comes out. And inside, we're going to have a sum over S. And here we have mu S, p pi, S prime. And this whole thing is multiplied with u squared S prime. So now we have to remember that we chose mu to be a stationary distribution under p pi. And the meaning of that is that if you start from mu, you make a step with the Markov chain, whose transition probabilities are given by p pi. If your initial distribution was mu, new distribution that you get after a step is also going to be mu. So that means algebraically that this is equal to mu of s prime. So this holds because of mu is a stationary distribution for the Markov chain defined by p pi. So you have sum over s prime mu s prime u squared s prime. And that's nothing but the mu norm of u squared. So now we have seen that p pi mu, p pi applied to u, the length of that squared is less than equal to u, the length of u. Okay, I don't try this mu. I haven't written it here, so I'm not going to write it there. So just to write it down. And then you can slash the square, take the square root of both sides. So we have that p pi is indeed a non-expansion, and we are done with the proof. Because then you can roll back, and you can continue here. So now we know that this is less than equal to u minus v. Okay. All right, so the proof is done. T pi is a gamma contraction with respect to mu, the mu norm. The composition of these two guys is still a gamma contraction. So it follows, corollary, that f, which is the composition of pi and T pi, is a gamma contraction with respect to the mu norm. So since it's a gamma contraction with respect to the mu norm, we can apply Banach's theorem. Banach's theorem comes with a condition with respect to what we call a norm. The norm has to be a norm. So far, we haven't talked about whether the mu norm is a norm or not a norm. The mu norm will not be a norm unless all the weights are positive, right? So to apply Banach's theorem, you need to have that mu s is positive for every s. It's not a norm if it's just not non-negative. If you zero out a bunch of states, then you can have many vectors. All those vectors whose corresponding component is non-zero, and the component where mu s is positive is 0, their norm would be 0. And in order to have a norm, you need to have the property that the only vector whose norm is 0 is a 0 vector. So you wouldn't have this property. And you could modify Banach's theorem to apply to this case as well. But if we just want to be strict, we want to apply Banach's theorem, then we have to remember we have to have this. Mu s has to be positive. So if mu s is positive, then we know that there is a unique fixed point. If mu s was not positive, the extension would say, OK, like you could have many fixed points. The iteration, whether it converges or not, OK, that's a separate question. It would converge, but you would need to argue separately that it does converge. So it's a much more complicated case to reason about when mu leaves out some states. So the simple case, mu is positive, Banach's fixed-point theorem applies, everything converges. TD, if it converges, has to converge to the fixed point of this operator as well. You can also see that TD might not, if mu is not positive everywhere, like you have to kind of separately reason about it. It's not trivial what to do in that case, but we're not going to do that. Okay, so good. All right. Time ran out. As kind of expected, we got to the fixed point. Once you have a fixed point, you can study how far this fixed point is from V pi. It's a triangle inequality. It's easy to get. You will see that the fixed point is not further than the best linear approximation than by a factor of 1 over 1 minus gamma. And we didn't have time for this, but somehow this whole TD business is very related to this idea of fitted Q iteration DQ. And maybe after I get back, I'll tell you about it. All right. There's a plan.